Good morning, everyone. Today we are going to talk about the complex integrations. And first, we will introduce the SCR, simply connected region. What is simply connected region? First, a region, say region D, bounded by a closed curve tau. And we say that this region D is connected if only two points A, B, that is in the region D, they can find a path, okay, that is lie entirely in D. So first, we call the region is connected. So what does that mean, connected? We have a curve, a closed curve. So suppose here we have a closed curve. Okay, this is tau. And the region D is bounded by this closed curve. So suppose inside this closed curve, I have a region D. And then we say that D is connected if only 2 points can find a path. So if I have 2 points, say A and B, here's A, and here's B. I can find a path. So here's the path. And this path is entirely in the region D. Then we call this region D is connected. Okay? So this is connected because I can find 2 points, and I can have 2 points and find the path that's still in the region D. The next is simply connected. We call the region D is simply connected if any closed curve tau, this tau now is in the region D. And then they can be shrink to a point without leaving this region D. So suppose I have a curve, let's say C. So if I have a closed curve, that's tau, and then I have a region D. Inside the region, I have a closed curve, C, say in this way. And they can be shrinked to a point. So this closed curve can be smaller, 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 smaller. And finally, I have a point that is still in the region D. Then it is called simply connected. So here is closed curve C. Any questions for this? Now you may ask, then what is not simply connected region? So if I still have a closed curve tau, this is my closed curve tau. Inside that is a D. But for this closed curve tau, here I also have a smaller closed curve inside. And then D is only with this kind of like a donut region. So in this case, if I have closed curve C, this is my closed curve C, then they can shrink, but they cannot shrink to a point because eventually they will shrink to another closed curve. Then in this case, if I cannot shrink to a point, then this is not simply connected region. Okay. All right, so based on this simply connected region, let us see the Cauchy integral theory. I have a complex function f of z. It is an analytic function on a simply connected region D. Then if tau is a closed curve in D, now this tau is in D, then if I do the circular integral for this complex function, then it will be 0. Okay, that means, for example, if I have a closed curve e to the z dz, that will be 0. If I have a sine z dz to the circular integral, then there's still 0. And z to the n dz, that is still 0, but here 0 for any non-negative integer. So suppose I have this, here is a region D. It is simply connected. So inside this simply connected region, any closed curve, for example, like triangular curve, if I have a circular curve, and if my curve is rectangular, or any shape, as long as it is closed, then the integration will be always 0. It really depends on your curve. Okay, so that means if I have a 1 over z, this function, if I want to do the integration, it can be either 0 or non-zero. Depending on, if it is 0, that means the closed curve do not include the origin, not enclosing origin. If this closed curve enclose or include the origin, then it is not 0. And here's another integration. We will prove that later, but you will see for this closed integral 1 over z to the n. This one is 0 for n greater than or equal to 2. And I really don't care about this curve enclosing the origin or not. Enclosing or not enclosing the origin. And also this n is a positive integer greater than or equal to 2. positive integer. And similarly, if I do the integration, you can see 1 over z minus a dz. This could be 0 or not 0. If this closed curve tau not enclosing, z equals a, that'll be 0. If it includes z equals a, then this integration is not 0. Any questions so far? It is either 0 or not 0. If it is not 0, then what is this integration? We will find out right away. And you can see that origin here, that will be in your singular point. Z equals a, that will be your singular point. If I include your singular point, then my integration is not 0. If not, then for the closed curve, and your integration is 0. Let's see why. Here we have the deformation theory that we can really try to find the circular integration. I have a tau and gamma that will be positively oriented closed path, so they are closed. And for the gamma, it is the interior of the tau. So tau is here and then gamma is inside. F is differentiable. This function is differentiable. What does that mean? Differentiable means that this complex number, complex function is analytic. So this complex function is analytic on the open set containing both paths and the set of points between them. So this is tau and this is gamma. And then for the integration, for closed curve tau, actually you can think of the circular integration with the closed curve gamma. Let's do this integration, then you'll know what deformation theory is. I want to evaluate this circular integration enclosing z equals 0, because when z includes 0, it is not 0. Well, when tau, this curve includes origin, integration is not 0. So what is this? Here I have closed curve tau, and then inside this closed curve I have a gamma. Here I have a gamma. And inside that it is a region D connected. So first let's plot. Suppose I have a closed curve. This is tau. And inside this closed curve I have a gamma. And let's just choose like circle. Easy to compute. This is gamma. And then I have a radius say gamma naught. Alright, so I want to do this circular integration. I can change that to this closed curve gamma. And this closed curve gamma, that is the magnitude of this complex number, will be the radius gamma naught, 1 over z dz. Now let's change the variable. Z equals gamma naught e to the I theta. Suppose z is the gamma naught, the radius, times e to the I theta, then dz will be I gamma naught e to the I theta, d theta. Right? So theta will be from 0 to 2 pi. So here 0 to 2 pi. And your z, 1 over z, and also this additional term. We have 1 over z, so 1 over gamma naught e to the I theta. dz will be I gamma naught e to the I theta d theta. So they cancel out. So I have 0 to 2 pi I d theta. Then you get 2 pi I. So it looks like your integration is either 0 or 2 pi I. So here we can write it down, this is 2 pi. Similarly, this should be 2 pi I. Alright. So if you want to guess, then you just guess either 0 or 2 pi. Then you can also see that for 2 pi I, that means I contain the singular point. If I have a singular point, then I do the circular integration. With a closed curve, then you'll get 2 pi I. But we just mentioned that in this case, no matter this closed curve includes the origin or not, then this is always 0. Let's see. We do the same thing. Okay, change the closed curve tau to gamma. This integration is equal to, for the deformation theory. And we don't prove those theory because here you just know that how to use that. One over z to the n dz. Say, no matter what closed curve you have, we can just shrink or make another small circle inside this closed curve. And for this smaller circle, we can change the variable to the radius and theta. So here we have integration from 0 to 2 pi. Do the similar, exactly the same thing. So I have a dz equals I gamma naught e to the I theta d theta. And 1 over z to the n. Z to the n will be gamma naught to the n e to the I n theta. So now rearrange it. I have I divided by gamma naught n minus 1. And then integration from 0 to 2 pi. e to the minus I m minus 1 theta d theta. And we have, if we do the integration, minus 1 divided by I times m minus 1 comma naught to the m minus 1 e to the minus I m minus 1 theta. Theta is from 0 to 2 pi. And you will see that when you plug in theta, you get 0. Okay. If you don't have any questions, let's see the extended deformation theory. Suppose I have more smaller closed curve gamma, like say gamma 1 to gamma n, and it is still positively oriented, and it is closed curve and closed path. Inside this tau. And there's no intersect, no overlap. Then to do the integration, we just sum all the smaller circular integration with respect to the smaller closed curve or closed path gamma 1 to gamma n. That means if I have here, this is tau, and I have gamma 1, this first. So I have gamma 1, gamma 2, gamma 3, gamma 4. For those 4 points, let's use this example. Wait a minute. To show this extended deformation theory. Okay. So first, let's just see this example, and then go back to see this extended deformation theory. I want to find the integration with a closed curve, tau. For this complex function, we can extract that into 2 parts. I have 1 divided by z plus I, and also 1 divided by z minus I. Okay, I have 2 parts. And it really depends on my tau. Okay, so now let's plot this closed curve tau. Suppose I have I and minus I. Suppose my tau is in this region, closed curve. Then you can see I have 2 singular points in this function. And for these 2 points, I can make a smaller circle. So here I have a smaller circle. Smaller circle, and we say this is gamma 1 and gamma 2. Okay, now according to this extended deformation theory, for closed curve tau, I can make smaller to only focus on these two smaller closed path or curves, gamma 1 and gamma 2. So I have two parts. First is for the gamma 1. So here's gamma 1. For gamma 1, we have 1 over z plus I minus 1 over z minus I dz. And the other part, maybe I just copy and paste. That will be your gamma 2. So we'll change here to gamma 2. Then we have four parts. First, for gamma 1, I have 1 over z plus I dz. And the second part is minus I over 2. And still in gamma 1, 1 over z minus I dz. So here I have closed curve tau. And for the gamma 2, we have also two parts. I over 2, 1 over z plus I dz minus I over 2, 1 over z minus I dz. And this is for gamma 2. First, what is the integration for the first part? 1 over z plus I with respect to the closed curve gamma 1. Your answer is either 0 and 2 or 2 pi I, right? So this is 0 or 2 pi I. This is 0 or 2 pi I. 0 or 2 pi I. And the last one, 0 or 2 pi I. So first, do you think it's 0? Raise your hand. 2 pi I, raise your hand. You only have these two choices. Gamma 1 is here. And z plus I is this point. So, is that 0 or 2 pi I? I have already told you that the answer is either 0 or 2 pi I. There's no, like, none of the above. So 0, raise your hand. 2 pi I. All right. So the first part, this integration is 0. Let's see. I'm doing the circular integration with gamma 1, okay, in this circle. And this singular point is here, right? It's not inside this closed curve. So this integration will be 0. Just like if, for this example, the singular point is 0, but if this closed curve does not include the origin, then this integration is 0. Otherwise, it is 2 pi I. Now, for this situation, gamma 1 is here, right? And then the singular point is this. For this closed curve, they don't enclose that singular point. So this circular integration will be 0. Okay? Let's see next one. How about this integration? 0 or 2 pi I. Again, if you think this is 0, raise your hand. 2 pi I. Now this time, gamma 1 here. And then singular point is I here. So they enclose this singular point. Then you can do the similar way. You'll get 2 pi I. So here we get 2 pi I. How about next part, the third part, for gamma 2, and the function is 1 over z plus I, 0 or 2 pi I. 0, raise your hand. 2 pi I. Last part, 0, raise your hand. 2 pi I. Yeah, so this goes to 0. Because now let's see this integration. I focus on the gamma 2, this closed curve. But the singular point, z plus I, it's here. And also I enclose this singular point. So after the integration, you'll get 2 pi I. But the last term, the closed curve, gamma 2 here, but your singular point is I. So this curve does not enclose this regular point, a singular point. So the integration will be 0. Then overall, you get 0. Okay? All right, if you don't have any questions, then based on this concept, we have the Cauchy integral formula. I have a complex function that is analytic, which means this function is differentiable in the region D, and there is a tau that is a closed curve in this region D. And for any point z naught in this tau, we have this formula. If we plug in z naught, actually that will be 1 over 2 pi I, and you take the integration. If you take the 2 pi I to the left hand side, then here is another formula you can see. You can also rewrite it to get your function f of z is 1 over 2 pi I f over Cauchy divided by Cauchy over z d Cauchy. Let's just see one example. This is f over z divided by z minus I. Okay, then I is your z naught. So here the answer should be, and also e to z squared, that is your function. This is analytic, right? It is differentiable for any points. Then you'll get 2 pi I f of I. And f of I is e to the I squared. That is 2 pi I e to the minus 1. Any questions for this? this is not complete actually. We should say, you should ask that where's tau, this closed curve, because this closed curve really affect your answer and also your integration. Okay, so this tau includes z equals I. If it is not, then that is 0, right? Z equals I here. I include that, and then I have a 2 pi I f of I. If not, if I have a closed curve here, then this integration is 0. For the higher derivatives, okay, this is the formula. Or we can rewrite this as the derivative of z for n times. Let's do this example. All right. For the circular integration, and this is your complex function, and tau is the closed path that does not pass through I. Then this will get, you have the integration, so we have 2 pi I times the nth derivatives. So 2 pi I divided by 2 factorial f double prime I. So you'll get so later on, that's just your basic calculus technique. You can check. The answer should be 3 pi I 3 plus 2I cosine 1 minus I sine 1. All right. So next we're going to talk about is the power series representation of the complex function. F is analytic. Again, that means F is differentiable. On the open disk D. About A, then I can write the complex function by the power series from 0 to infinity, the n from 0 to infinity, coefficient times z minus a to the n. I have nth power. Okay, and what is the coefficient Cn? Cn, there will be the nth derivative of your complex function, and then replace your your complex number by a. Divide by n factorial. And for this coefficient, we call the Taylor coefficient. And Taylor coefficient for an analytic function is unique. So once you find this coefficient, you cannot find another one that's different. It should be always the same because it is unique. For example, how do I expand this complex function? About z equals minus 3i. Now here is a little different. this is z equals minus 3i here, minus 3i. I want to expand this this complex function. So that means I should have z minus 3i, that means z plus 3i to the n. Okay, I want to create this term. Okay, so to create this term, then we need to rearrange this original complex function. Original function, that is 2i divided by 4 plus iz. And I need to create z plus 3i. So I have a z plus 3i. In this case, and I need to times I because here I have iz. And then plus 7. Because I times 3i, that will be minus 3. Plus 7, I will get 4. So they are equal. Okay, and the next step, I would like to make the ratio. So here I take the 2i over 7 outside. And then we have 1 divided by 1 plus I over 7 z plus 3i. Remember, 1 over 1 minus ratio, that is the summation, n from 0 to infinity, r to the n, r to the n, the ratio to the n. So now I'm trying to make this to like 1 minus r. I try to find the ratio. So in this case, z plus 3i is less than 7. And this 7 is radius of convergence. So now we can rewrite this fraction to still keep 2i over 7. And then 1 over r, 1 over 1 minus r. I get the summation n from 0 to infinity. And from minus 1 to the n. And then your ratio, I over 7 z plus 3i to the n. 1 minus I over 7 z plus 3i. This is your r ratio, right? For this ratio, so you ratio to the n, this to the n. So that's why we have minus 1 to the n, and also the rest part to the n. Okay? Then you have a summation n from 0 to infinity 2 times minus 1 to the n, I to the n plus 1 divided by 7 to the n plus 1 z plus 3i to the n. So this function will converge if this ratio is less than 7. So if I minus 7 z plus 3i is less than 1, So we have minus 3i and plus 7, we will get 4i. Those are the singularity. And between here there will be, okay, then between this, the radius is 7, and this function converges. Because for this equation, your ratio should be less than 1. Okay, if your ratio is not less than 1, then I cannot write, well, they will diverge. Okay. So this is our ratio. All right. Any questions for this? All right, so now for this power series, if you don't have any questions, then let's talk about the Laurent series. Because what if I want to make the series with the singular point? So far here you can see that there's no singular point. But how about some singular points? Can I still make an expansion? So you can see that page 17, we have another series called Laurent series. For the Laurent series, we remember that f of z, this complex function, is analytic here in this region. And we have the power series or Taylor series representation. But what if this function has some singular points in this R? Then what should we do? We need to consider the complex function with an annulus, like a donut. If we plot this annulus, it looks like here's A, and then this is R naught. And here's R1. And we can only consider this ring. All right. And here we say that the Taylor series expansion about A, this A is differentiable. If this A is not differentiable, then we need to consider the Laurent series. So here we can have a note. The Taylor series or Taylor expansion. Taylor expansion about A. And this A is differentiable. If we want to have an expansion about some point and that point is not differentiable, then let's see Laurent series. So we can represent this complex function by the power series. And this power series is a little bit different. You can see that this is from, n is from negative infinity to infinity, rather than 0 to infinity. Okay. And if I have this function, this summation from negative infinity to infinity, if we expand that, then we have the coefficient with minus number until the positive number. And overall, this is, you can think about this expansion into two parts. N from minus infinity to minus 1. Cn z minus a to the n. And also our Taylor series part, n from 0 to infinity, Cn z minus a to the n. So this is the Lorentz part. And the second term will be the Taylor series. For example, e to the 1 over z. That'll be 1 plus 1 over z plus 1 over 2 z squared, and so on. And your z is from 0 to infinity. This you can think of e to the 1 over z like e to the w, or e to the w will be 1 plus omega plus w plus 1 over 2 factorial omega, w squared, and so on. You just change w to 1 over z. And for next one, cosine z divided by z squared. We know cosine z. We just give them the definition. What is cosine z? Here's a cosine z. Okay. N from 0 to infinity. Okay, so that's plug in. N from 0 to infinity minus 1 to the 2n divided by 2n factorial times z to the n. This gives you 1 over z squared minus 1 over 2 plus 1 over 24 z squared. And 1 over 720 times z to the 4th. And then the annulus is that the z, so far here the z is between 0 and infinity. Now if I want to have an expansion, here expansion of this function about minus I, like a is equal to minus I. Here 1 over 1 plus z squared, you'll get this is z plus I and also z minus I. Now I want to expand that with about minus I, then here I have a singularity. Once I have a singularity, then how can I expand this function? Let's see. First, we need to know that 1 over 1 plus z squared, that's I over 2, 1 over z plus I, and minus 1 over z minus I. We need to deal with this part, but here, this part, this is just our regular function, and I want to expand this function about z equals minus I. This singular point is z equals I, but here I want to expand that with z equals minus I. So it doesn't matter. There's no singularity for this part. So here we can rewrite the second part into the Taylor series form. So how do I do this? Now, for this part, 1 over z minus I. Remember, we need to create the ratio. So here, n from 0 to infinity, r to the n, the ratio to the n will be 1 over 1 minus ratio, and this ratio should be less than 1. The magnitude of this r should be less than 1. So now I need to create 1 minus r. And also this is the expansion about z. A equals minus I. So z plus I equals 0. Then that is the expansion about minus I. So we need minus 2I to compensate. And for this part, you have minus 1 over 2I. And then here you have 1 divided by 1 minus ratio z plus I divided by 2I. And this is a ratio, then we can write a summation. 1 over 1 minus r, there will be summation n from 0 to infinity, and your ratio to the nth, z plus I divided by 2I to the n. So for this part, once you get the summation, that means your ratio should be less than 1. Z plus I divided by 2I. This magnitude should be less than 1. Then you have minus summation n from 0 to infinity, 1 divided by 2I to the n plus 1, and z plus I to the n. So this is our second part. Okay, this is our second part. We can rewrite this complex function 1 divided by 1 plus z squared. First term, I over 2, 1 over z plus I, and then second term will be I over 2, summation n from 0 to infinity, 1 over 2I to the n plus 1 times z plus I to the n. So this is the Lorentz part. And here is Taylor series. And we should know that 1 over 1 plus z squared. Then your z equals I and minus I, they are not analytic because they are singular points. And for z equals minus I, we need to find the ratio. The ratio should be less than 1. Again, why ratio should be less than 1? Because for this formula, once r is less than 1, for this summation, that will be 1 over 1 minus r. So z plus I divided by 2I, this ratio should be less than 1. We have z plus I is less than 2. So here is our annulus of convergence. Z plus I is between, the magnitude should be between 0 and 2. So if you plot, here is I and I, y. I have minus I and I. The radius is only 2. Okay. Let's do one more example. If you don't have any questions, then let's move on to page 24 and page 23. All right, so now the complex function is analytic in the annulus. And then the gamma is a closed path about A, and this path is lying entirely in the annulus. We can find this coefficient. This coefficient will be in this form. Okay. Let's just find the Laurent expansion about this function. Every time when you see the expansion, you need to care about where. Okay. Now I want to find the expansion about z equals minus 1. Then you need to check if z equals minus 1 is a singular point in your function. And here indeed, this part will go to 0. So this part will be the Laurent part. And the rest we can write it down as a Taylor series. Okay. Before we do that, for this coefficient Cn, that is the Laurent expansion of your function about A. And then for the Laurent expansion, we need to, here's a note. This complex function need not be differentiable at A. Or even define. Okay, so now let's see this Laurent expansion. We know, we've seen that Z plus 1 here, it is not differentiable. So this part will be the Laurent part. Then the rest, this one is fine. We will get this as express this as a Taylor series expansion. So first, let's extract this function into two parts. 1 over Z plus 1 times Z minus 3I into two parts. One is 1 over Z plus 1 part, and then the other one is Z minus 3I. 1 over Z minus 3I part. Okay, and then the coefficient here. This is the coefficient. Apparently, this will be the Laurent part. And then we need to deal with this Taylor series. For the Taylor series, 1 over Z plus minus 3I. Let me give you 3 minutes to see if you can find the Taylor series or Taylor expansion about 1 over Z minus 3I. Okay. You can find the ratio, and ratio should be less than 1. Then you can find the radius of convergence. So to find the ratio, let's see. We need 1 over 1 minus ratio, right? And also we need Z plus 1. Okay. We need Z plus 1 here. So eventually you need 1 minus Z plus 1 divided by something. So you will get, this is 1 plus 3I. Here's 1 plus 3I. Try to create Z plus 1. Because we want the expansion about Z equals minus 1. So we create Z plus 1 here. Then this is 1 over 1 minus R. And we need to make sure that this ratio should be less than 1. Then we can have the summation. Summation Z plus 1 divided by 1 plus 3I to the n. And here n is from 0 to infinity. Then we have minus summation n from 0 to infinity, 1 divided by 1 plus 3I to the n plus 1, and Z plus 1 to the n. And then the radius of convergence is the magnitude between 0 and square root of 10. Okay? And we say that singular point, that is the point that makes the denominator 0. And for singular point, sometimes we also call that is poles. So poles or singular points, that means we need to care about the denominator to see if the point makes the denominator goes to 0, then that is the singular point or the pole. So back to page 18, let's see the poles. In the Laurent expansion, you can see that A here, z equals A will be the singular point, and we also call the pole of the function of z. So z equals A is the singular point. And we also call that pole for the function of z. And then we have the classification of poles. And here is just tell you that the name of that poles. Okay. So if this complex function terminates at finite negative power term, for example, f of z equals c to the minus m to the z minus a to the m, and c to the minus m plus 1 to the z minus a to the m minus 1, and so on. C minus 1 to divide by z minus a plus c naught and c1, z plus a and z minus a. And since we have z minus a to the mth, I have nth power, we say z equals a. This is pole of order m. If m is just 1, then we say this is a simple pole. If m goes to infinity, then we say z equals a is an essential singularity. And here we should notice that the c minus m, this is not equal to 0. And my m is positive. So for the function cosine z divided by z squared, we have this as 1 over z squared minus 1 over 2 plus z squared over 24, and so on. Then you can see that we have z squared. So we said z equals 0. Is a second order pole. And the next one, 1 over z plus I, then we can say the function f of z has a simple pole at z equals minus I. And f of z equals z to the 1 over m. We can rewrite that as summation n from 0 to infinity 1 over n factorial z to the n. This function has an essential singularity at z equals 0. And the last one, sine z over z. Okay, if you expand that, we have 1 minus 1 over 6 z squared, and so on. Then we say that z, and actually there's no, if you expand that, there's no singular point at 0. Even though we think, okay, this one maybe have a singular point 0, but actually there's no z in the denominator. So z is 0. We say this is a removable singularity. Of your function f of z. All right, any questions? And how do we check the order of poles? In this case, this is a simple case, but if I have complicated denominator, and how do we decide the order of poles? So here, we can check the complex function has a pole of order m at z equals a. Okay, very important, at z equals a. If z equals b, c, or other numbers, then the pole of order may be different. Okay, so I say that the pole of order m, if I do the limitation, and I times z minus a to the m, nth power times the complex function, if this is a non-zero constant, then I will say that this is a pole of order m. We will see some examples. If for the poles of products, I have a complex function, and I say it is a pole of order m at z equals a. And also, another complex function has a pole of order n at z equals a. When they times together, then the pole of order will be the summation m plus n, again at z equals a. If it's z equals b or c, then your pole of order will be different. And we also have a cancellation of zeros and poles. So if I have a pole of order m at z equals a, and another complex function, I have a zero of order. Zero that will be in the numerator, and that is the zero of order n. Then they have a pole of order cancellation. Well, they have the cancellation of zeros and poles, and your final pole of order, your final pole of order will be m minus n. So here I have a pole of order 1. No. I have a pole of order 2 at z equals minus I. and I have a 0 of order 1, and still at z equals minus I. So the overall, the pole of order will be 2 minus 1. Okay, at, very important, pole of order 1 are where? At z equals minus I. Okay, see this example. Cosine z divided by z to the fourth and z plus I squared. Then if we focus on this part, z equals minus I. So z equals minus I, then it is a pole of order 2, double pole. And how about z equals 0? Z equals 0, pole of order m, so we can add z equals 0. So I'll have limit z goes to 0, z minus 0 to the how much? F of z. And this, I will get a non-zero constant. I will get a constant c. Okay, so here I have a z to the something, and then z to the fourth, z plus I squared cosine z. At least this question mark should be 4, right? They'll cancel out. And we will replace z to 0. Then I have cosine 0 and I squared. And this is non-zero constant. So this is, at z equals 0, I have a pole of order 4. Okay? Then what is the pole of order here? Sine z divided by z squared. First, we can take the limit. Z goes to 0 because we know that z at 0, that is the pole. And that will make your fraction to be divergent. Because if your denominator is 0, then it goes to infinity. So z goes to 0. If I just times z first, f of z. Here z is z minus 0. Okay. And we just check order 1, pole of order 1, and see if it is a non-zero constant, then this is a pole of order 1. So we get limit z goes to 0, sine z divided by z. This use L'Hopital's rule. I will have cosine z divided by 1. And then finally when z is 0, then you get 1. It is a non-zero constant. So this function has a simple pole. And a simple pole where at z equals 0. Okay, any questions for this? Because you see, if z goes to 0, what happens to here? Sine 0 is what? Sine 0 is 0. And then denominator is 0, and you take limit. 0 divided 0, I use L'Hopital's rule, so I take the derivative. I got cosine z over 1, and take limit z goes to 0. Then we get 1, right? I need to check. Right, I need to check the order of poles. How do I check? This will be z minus 0 to 1 times f over z. And take the limit, z goes to 0. Now my a is 0. Okay. If you don't have any questions, then we will move on to residue theory. To talk about the residue theory, first we need to define residue. What is a residue? I have a complex function, and the complex function with the isolated singularity at z equals a. Isolated singularity, that means f of z is differentiable in the region, in this certain region, because it's z at z equals a. Okay, so in this region it is differentiable, but not at a. Itself. So it is differentiable here, but not that specific point at a. Only at a it is not differentiable. So in this case, then we can express the complex function by Laurent expansion or Laurent series. Remember the Laurent series? I have a Laurent's part plus the Taylor series. Okay, so here's the Taylor series, and the Laurent part is with the coefficient, with the negative coefficients. So in this case, if I express the complex function with a Laurent expansion, then c minus 1, this coefficient is called residue, and we define it as residue. So c inverse 1 is residue. And this is denoted we will write the residue, the function at a. And how do we get those coefficients? For the Laurent coefficient, here's the definition of the Laurent coefficient for general case. Okay, and then we can check the minus 1. So if we put n equals minus 1, I have 1 over 2 pi I times the circular integration, which means this circular integral f of z dz, that'll be 2 pi I times the residue. Okay. So depending on your closed curve, if they include the singular point, then my integration will be 2 pi I times the residue. If we have more than one singular points, then here is a residue theory. I still have 2 pi I, but 2 pi I times the summation or the collection of your residues. If I have 3 singular points here, then the integration will be 2 pi I times this residue plus this residue and this residue. Okay. So let's see. Well, we will see some examples. How do we find the circular integral? But before that, how do I calculate the residue? Okay, so how do I calculate the residue? There are two ways. First, if I have a simple pole at z equals a, then my residue will be the limit. You have z minus a times your complex function, and that z goes to a. If your function has a pole of order m, not just a simple pole, then your residue will be 1 over m minus 1 factorial, and then times this fraction, and that the z goes to a. First, let's see this complex function. At z equals minus 4i, this is a simple pole, right? I'm talking about z equals minus 4i, not z equals 2. Z equals 2, there will be a double pole, correct? How do I know this is a simple pole? Because I need to times z plus 4i and the function, and then they can cancel out, and then you plug z equals minus 4i, you get a constant. So this is a simple pole at z equals minus 4i. Then your residue, the residue is just like the constant you got, because we take the limit, z goes to 4i minus 4i, and you have z minus 4i, or z plus 4i, times your f of z. You get minus 10i divided by 2 plus 4i squared. And you can see that this is a constant, non-zero constant. Okay, let's see the next example. I have 2iz minus cosine z divided by z cubed plus z. Let me give you 2 minutes. Just tell me that what are the poles in this fraction. And also you can determine that this pole is a simple pole, double pole, or a pole of order what? Then first, how many poles do we have? 3. And what are they? 0?
Minus I.
Yeah, okay. So to get these 3 poles, actually we have z times z squared plus 1, right? And 2iz minus cosine z. And then do the, we still simplify it to see 3 poles. We have z plus I, z minus I, 2iz minus cosine. So I have 3 poles, 0, minus I, and I. So this function has simple pole at z equals 0, minus I, and I. So please find the residue. Residue at z equals 0, residue at z equals minus 1, minus I, and residue at z equals I. First, please find the residue at z equals 0. What is it? Since it is a simple pole, okay, So what is your residue? -1, right? So how do you get -1? Yeah. So I have a function and at 0, which means the limit z goes to 0, z minus 0, which is z, times f of z. So if I times z, they'll cancel it. And you plug in z equals 0, you'll get minus cosine 0 divided by 1. So that's -1. And how about the residue at I? Similarly, z goes to I. And we have z minus I times your function. We have -2 minus cosine I divided by -2. And the residue at z equals -I. And we have z plus I times f of z. f2 minus cosine minus I divided by -2. All right, so now, any questions for finding the residue? Now let's do the circular integration. So here, when we do the circular integration, every time you need to ask yourself, where is the closed curve? So in this case, we have three simple poles, 0, I, and -I. Then I want to do the circular integration. I have two different curves. This is gamma 1.
Why we have two curves only?
The what?
Why we have only two curves? Like
Two curves?
3 or
We can have 3, 4, 5. Well, I'm doing the circular integration, right? It depends on my curve. And so far, I just have 2 curves. You can have more. And suppose I have a curve. Suppose we just have a curve 1. Yeah, I think that'll be okay. Now this is my curve, gamma 1. So what is the integral? The circular integral here. We check first, the curve is here, okay? Inside the curve, see the residue theorem. Inside the curve, actually it is analytic, except I, 0, and -I. Because this, here, I, 0, -I, because they are poles, and they will make this function go to infinity. So for these 3 points, by the residue theory, I should have 2 pi I times their collection, their summation. Okay? So this should be 2 pi I. And we have let me see. Here I may write the residue at 0, and residue at I, and also residue at minus I. Then you'll get 2 pi I minus 1 plus cosine 1 hyperbolic of cosine. Okay, for gamma 1. First, this function, for the numerator, it is analytic at all 0. Right. But if I have a denominator, it is analytic except 0, minus I, and I. These 3 points. Okay, and then my curve includes these 3 points. So this circular integration will be 2 pi I times the summation of those 3 residues. Okay? If I have a curve gamma 2, then let's find the integration. Let's see, I can design. Okay, so for gamma 2, what is the answer for this circular integration?
For gamma 2, we only take 2 of them, right? 2 of the residue values. Or like, which one we going to choose?
Then you tell me.
Like we have 6 options then.
6 options.
Like 6 answers for gamma 2.
Second. Well, for your gamma 2, you see, gamma 2 is here. Okay, these blue curves. Okay, so I only care about this. Inside this curve, I still have f. And f is analytic except where? 0 and I. So except 0 and I for the residue theory, except the 0 and I. Then here I have 2 pi I times their collection, 0 and I. So here I have 2 pi I. I only need to consider residues at 0 and the residues at I. Okay?
But like we find it by ourselves because we draw the graph. So
Yeah, so
does it give us some graph or something constantly determined?
yeah, so every time, as I said, that when you find the integration, you need to care about your closed curve first. So if I have a closed curve, this, what is the circular integration?
Minus I and
2 pi I times the residue at I, and also 2 pi I times the residue at minus I, right? If I have this curve, then my circular integration will be 2 pi I times what? The residue 0 plus the residue at minus I, right? Okay? If I have this curve, what is the circular integration? So for this curve, 2 pi I times the residue at I and the residue at Z equals minus I. Okay, if I have a closed curve at origin, then what is the circular integration? 2 pi I times the residue at 0. Okay. All right, so now we have 4 minutes, and then for this example, again, just try to find the residue. Okay, first you need to determine how many poles do we have. 3 poles at where?
0, 2i, minus 2i.
Okay, and what kind of poles do we have? Is a simple pole, double pole, a pole of order 3, 4, 5? So we will need to find the residue at 0, 2i, and minus 2i. And yes, we have a simple pole. At z equals 0, z equals 2i, and z equals minus 2i. How do you find the residue at z equals 0? Limit still z minus 0 times your f of z, and that z goes to 0. You have sine z divided by z divided by z squared plus 4. Okay? And you get 1/4. And residue at 2i, you got limit z minus 2i times f of z, and z goes to 2i. So you have sine z divided by z squared times z plus 2i. You got minus I over 16 times sine 2i. And similarly for the residue at minus 2i, we times z plus 2i and your function f of z. Then you have sine z divided by z squared, z minus 2i. And then you have minus I over 16 divided by sine 2i. So you have 3 poles, 0, 2i, and minus 2i. Then depends on your curve. Okay, depends on your curve, your circular integration will be different. All right, let's see this case. What is the residue at minus I? Because at minus I, z at minus I, it will make this fraction go infinity. Okay, because there'll be 0 in the denominator. But first we need to find out how many poles do we have. This is a pole of order 3. Has a pole of order 3. Pole of order 3, where? We always need to tell people that it is at minus I. Otherwise, it is not a pole of order 3. then we can get the residue. Will be 1 over 2 factorial. Limit z goes to minus I, and I take the derivative. And times z plus I cube, so that I can cancel out the denominator. How do we find the residue for pole of order more than 1? You can see here, the trick is I want to cancel out your denominator. So for the simple pole, f of z, there will be something divided by z minus a. So I times z minus a, something z minus a. So I can cancel it. Okay, but how about the pole of order m? It's not 1, it's 2 or 3 or 4 or even more. I still want to cancel out your denominator. Okay, so you will times z minus a to the m, divided by that. And others will be just m by 1, take the derivative of m by 1. And then you have a factorial, 1 over m minus 1 factorial. Okay, so how do you remember this? Remember that I have to cancel out the denominator when z goes to a. Otherwise, your fraction will still go to infinity. So I need to cancel this part. So that's why here it is a pole of order 3. So I times z plus I cube. And definitely because this is my f of z. So I can cancel this. Okay, once I cancel that, for pole of order m, you need to take 1 over m minus 1 factorial. And also you take the derivatives m minus 1 times. Okay. All right, any questions for this? Then how about this circular integral? Okay, for the circular integral, let me give you 5 minutes to do it. Anyone get the answer? Then I'm curious that what are you looking for? So let me randomly ask someone that what are you calculating for this question so far? You find the poles, and how about here? What are you looking for? You find the residue? Why do you need to find the pole and find the residue? All right, okay, stop. Do you really need to find the pole? Or do you really need to find the residue? Why? Why do you need to find the residue? Why do you need to find the pole? Why don't you just ask me, for your circular integration, what is the gamma? Where is the gamma? You don't know the gamma, then if my gamma is here, the answer is 0. here there'll be 0, right? It really depends on my gamma. I haven't given you the gamma, then you should ask, where's gamma? Okay, for this curve, right? So suppose, why do you need a gamma? You can see we know there's a pole minus I and minus 2I. Now let me give you the gamma here. And then what are you going to find now? We know we have a pole at minus I and minus 2I. And then close here, so only minus 2I included. I only need to find the residue of minus 2I. And then the answer will be 2 pi I, the residue. If I have a closed curve here, your integration is 0, right? If I have a closed curve here, your answer is 2 pi I residue at minus I. If I have a closed curve including minus I and minus 2I, then my answer will be 2 pi I, the residue at minus I, and also I need to consider the residue at minus 2I. Right? So now I only includes minus 2I, and we can observe that minus 2I is a pole of order 3. So the residue F and minus 2I order a pole of order 3. So there'll be 1 divided by 3 minus 1 factorial. And then have a limit z goes to minus 2I. And take the derivative twice. Because I need to cancel out the denominator z plus 2I. So I need to times z plus 2I cube and the function. So here we get 1 over 2 e to the minus 2I, 2 minus I. Then your circular integration will be 2 pi I, the residue, your function at z equals minus 2I. That is pi I, 2 minus I, e to the minus 2I. Okay. But meanwhile, we can also find the residue at z equals minus I. If I include these two singular points, then I also need to find include the residue. So at z equals minus I, I have z plus I times the function, and you get I e times e minus I. But in this case, we don't use that, okay? Because it depends on your gamma. It depends on your gamma. Where is our gamma? My closed curve only includes minus 2I, this singular point. I don't include minus I.
How do you know gamma?
I decide. You can decide. For this example, I just decide my gamma is here. Maybe in the exam, my gamma is this, and my gamma is here, or my gamma is here, or my gamma is here.
So like in the exam, you're gonna show us some probability.
No, not just exam. Every time when you do the integration, you need to know what this gamma is. You need to ask yourself, I'm doing the circular integration, great, but where? Right, and this time I give you the gamma here. If I give you gamma, this circle, then I need to include this two, because these two singular points are inside my curve, my closed curve. If I have a gamma here, what is the answer? 0, right? And also we know that those are simply connected. Okay, those functions. So, and those functions are analytic, especially e to the z. So that's why if I take the closed curve, not including minus I and minus 2i, then the integration will be 0. Remember, this is from the Cauchy integral theory. Okay, any questions for this? Then we have so many exercises that you can practice. Okay, so every time you see that my gamma is different, so based on your gamma, then you need to find the circular integration.